All right, so here's our first equilibrium example. So we have in figure 12-5A, a uniform beam of length L and mass M equal to 1.8 kilograms, so it's the mass of the beam, is at rest on two scales. A uniform block with mass big M equals 2.7 kilograms is at rest on the beam with its center at a distance L/4 from the beam's left end. What do the scales read? All right, so we have to find basically the normal forces from both the scales because that's always the scale reading, right? The normal force. Now, here we have equilibrium. We have a static equilibrium because nothing's moving here, right? It's all at rest. So in static equilibrium, the trick here is that the net force equals 0 and the net torque equals 0. Okay, so let's draw the forces on here that are acting on this system, and then we'll go from there. So first and foremost, we have the force of gravity from the beam. So we'll call this FGB. Oh man, we have beam and block. So we'll call this FG, I don't know. We'll call this little m when we talk about that. That's really annoying. I hate when they do that. And then this is the force of gravity of the block. So we'll call this big B, and then we'll call this little b for beam because the beam is less mass than the block. All right. So we also have the normal forces that we're actually trying to solve for. So this is going to be the normal force, and we'll call this the right side. And this is F normal on the left side. We can also just call that F left and F right, but whatever, it doesn't matter. Okay, so we want to find those scale readings. So we want to find this normal force and this normal force. Those are our two answers. So first and foremost, we know, again, this is equilibrium, so therefore our net force is 0. So what I mean by that, net force on this object is equal to 0. I literally did net force net. That's very redundant. You don't need both the sigma and the net. I'm sorry. So net force equals 0, which means the up forces are going to equal the down forces in this case. So therefore, my normal force on the left plus the normal force on the right minus the force of gravity of the block minus the force of gravity on the beam, that's all going to be equal to 0. Now, of course, force of gravity we know is just mass times acceleration of gravity. We know both the mass of the block and the mass of the beam, so we can plug that stuff in for those two things, but we have two unknowns here, right? We don't know both the force left and the force right. Those are the two things that we're trying to find in this problem. So because we don't know that, we're going to have to use net torque equals 0 as well, okay? So force of gravity on the block, that's going to be big mg, and then force of gravity on the beam, that's going to be little mg, and then we can plug that information in as well. Big M, the mass of the block, was 2.7 kilograms times 9.8 meters per second squared, minus little m, the mass of the beam, was 1.8 kilograms times 9.8 meters per second squared. And that's all going to equal 0. Whoa, 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 whoa. So here we get 2.7 times 9.8, and then 1.8 times 9.8. So we're subtracting a total of 44.1 newtons. And that equals 0. So we get force left plus force right equals 44.1 newtons. So again, we have two unknowns still here. So because we have two unknowns, we're going to have to use the net torque equals 0 as well, because that's the other requirement for equilibrium. So net torque is also equal to 0. And when we look at this here, what we want to do here is we want to put our axis of rotation somewhere where one of our unknowns is, one or more of our unknowns, as you'll see as we go forward, so that we can kind of cancel that out. Because obviously, if a force is at the axis of rotation, there's no R, there's no moment arm for torque, so therefore there is no torque from that force. So what I mean by this is we're going to put our axis of rotation right here, at that left-hand side there, and then say that that thing, we're measuring the torque about that axis of rotation, and that net torque equals 0 about that axis of rotation, because obviously we're not moving. But that normal force on the left-hand side then would cause no torque on the object. So that's going to be a 0 for that. So that way we can find the normal force on the right-hand side from that equation. Okay, so what we're going to do here, now we're going to say, okay, the torque from the force of gravity of the block, and the force of gravity of the beam, and the normal force from the right-hand side, or that scale, that net torque, adding all those torques up, is going to be 0. Now we have to find which ones are going to be positive, which ones are going to be negative. If you see that the force of gravity of the beam and the block, they're both pulling down on that system. So since they're pulling down on the system, they would cause a clockwise rotation. So those are actually both negative torques. And then the scale over here is pushing up on the system, so that would cause a counterclockwise rotation. So since it's a counterclockwise rotation, that would be a positive torque. So what we're going to get here for our net torque is we get, and we can just also include the torque from the left-hand side right now, and I'll show you how it ends up being 0. So we're going to get torque from the left-hand side plus torque from the block plus torque from the beam plus torque from the right-hand side. And then, like I said, these two are both going to be negative. Okay, so I'm going to actually plug that in next. And then we know that torque, in this case, we're using the RF sine theta equation for torque. So you have to have a moment arm in order to actually have a torque. So because of that, there's no moment arm for this force right here. There's no R value, right? We're not any distance away from the axis of rotation because that normal force is at the axis of rotation. So this whole thing is 0 in that case. So what we end up getting here is net torque is equal to negative torque from the block, like I said, because it would cause a clockwise rotation, minus the torque from the beam. Again, it's negative because it would cause a clockwise rotation, plus the torque from the right-hand side. Now, we know that this all equals 0, and now we can plug in that equation for torque, all right, for each of those things. So we get negative R, or moment arm, so our distance from the axis of rotation to the block, times the force of gravity of the block, times the sine of the angle, which we'll talk about in a second, and we'll just call that angle block, minus moment arm to the beam, times the force of gravity of the beam, times sine angle beam, plus moment arm to that right-hand side, times the force, normal force right-hand side, times the sine of the angle to the right-hand side. Now let's talk about those moment arms and the angles. If we look at these angles here, the moment arm for, say, the block right here, we can see, is that going to be that distance right here. Now the angle between that moment arm R and the force is going to be 90 degrees. And that's going to be true for all of these, right? That distance between the axis of rotation to the force, that's our moment arm. And then we can see also the angle between the moment arm and the force is 90 degrees for every single one. So because of that, all of these signs here, sine of this angle, sine of this angle, sine of this angle, all ends up being 1 because all of those angles are 90 degrees in this case. So that kind of cancels out, just ends up being 1. So we just end up getting 0 equals negative RB, force of gravity of the block, the beam, and then of that right-hand side. Okay, so it's getting simpler and simpler. Okay, our next step is we need to find what those moment arms are. So I know that the block is, it says the block is a center, rests on the beam with its center distance L/4 from the beam's left end. So this right here is going to be L/4. The beam, that center of gravity of the beam is going to be in the very center of the beam. So the R for the beam is going to be L/2. So just the total length divided by 2 because it's in the very center. And then, of course, this force over here is a distance L from that axis of rotation. So what we can do here is then plug those in for our R values. And then we can also plug in our mass times acceleration of gravity for those two forces of gravity. So what we end up getting is 0 equals a negative L/4. And then the force of gravity of the block is going to be the mass of the block, which ended up, well, let's just put big M G for now, minus the moment arm for the beam, which is in the very center. So that was L/2 times little m G plus big L times force right. Now here, what we're going to do here is we're just going to divide everything by L, so that L just cancels out. We divide both sides by big L. So we end up getting 0 equals negative 1/4 times big M, the mass of the block, which was 2.7 kilograms, times G, 9.8 meters per second squared, minus 1/2 times little m, which was the mass of the beam, which was 1.8 kilograms, times 9.8 meters per second squared, plus 1 times the force right. All right, so now we get 1/4 times 2.7 times 9.8, and we get a negative 6.615 here, newtons, minus 0.5 times 1.8 times 9.8, we get 8.82 newtons plus Fr. Adding both of those things to the other side, we get 6.615 plus 8.82, and that ends up being our force right is 15.435, so about 15.4 newtons. So that's our answer for the right scale reading. And then now that we have that, we can then plug it back in way up here to find our left scale reading. So what we end up getting here is force left plus that 15.4 equals 44.1 newtons. And so we end up getting that force left, or our left scale reading, is 44.1 minus this answer, which is about 28.7 newtons. So left scale reading was 28.7, right scale reading was 15.4